Hello students, this is a review for exam 1 on waves, sound, electric field, electric potential and capacitance. Or if you study this, you are sure to do good on the exam. But studying this does not mean that you memorize the questions. That will be of no use, because the questions are not going to be exactly identical to what I've given here. So you got to really understand, and then you will do good on the exam. All right, let's jump into the first question here. The first question talks about how many electrons need to be removed to give an object a charge of 1 nanocoulomb. So you know that if electrons are removed, an object becomes positively charged. And if electrons are added, then the object becomes negatively charged. So the question here is how many electrons? So we're looking for the number of electrons to be removed from an object to give it a charge of 1 nanocoulomb. First of all, a nanocoulomb is 10 to the negative 9 coulombs. So you got to know the difference between a nano and a microcoulomb. Micro is 10 to the negative 6 and nano is 10 to the negative 9. So in this case, it's 10 to the negative 9. And so that's 1 nanocoulomb. That's 10 to the negative 9 coulombs. The charge of the electron will be given, but it's good to know it's 1.6 times 10 to the negative 19 coulombs. The formula is Q is N times E. And so we're looking for N. Q is given. N is what we are trying to find. E is 1.6 times 10 to the negative 19. And divide both sides by 1.6 times 10 to the negative 19. And we will get the answer. So that's going to give 1 by 1.6, which is 6.25 times 10 to the 9 electrons. Okay, so 6.25 times 10 to the 9 electrons need to be removed to give the object a charge of 1 nanocoulomb. The second one talks about a sphere. This is a sphere that is charged, and the charge is spread all over its surface, and that is the property of any sphere. And the total charge on that surface is given. It's 2 microcoulombs. And we are asked to find the electric field 4 centimeters outside the sphere. So what is the electric field? That means what is the strength of the electric field 4 centimeters away from the surface of the sphere? So the most important thing here is to understand that the charge on the sphere behaves as if it were all kept at the center. So the entire 2 microcoulomb is assumed to be kept at the center of the sphere. So which means it's kept at O. And so the distance to P would be 10 centimeters. 6 plus 4, 10 centimeters. And now we can use the formula for electric field due to a point charge, because all the charges are now kept at a point O. Just remember that the distance is 10 centimeters, which has to be changed into meters. Here's the formula, KQ by R squared. K is the constant. It's 9 times 10 to the 9. Q is 2 micro. See, notice micro is 10 to the negative 6. And the distance is 10 centimeter. 10 divided by 100 gives 0.1 meter. So when we put that as the distance, and do not forget to square it, and then you do the calculations, you are going to get 1.8 times 10 to the 6 Newton per coulomb. That is the unit of electric field. All right, again, so remember that just imagine that all the charges are at the center of the sphere and use the formula for field due to a point charge. Number 3, we have, let's run that, electron moving in a field of intensity 100 Newton per Coulomb. So the electron, as soon as it enters the field, a force will act on it. And because of that, the electron will be accelerated. We are asked to find the acceleration of the electron. So from what I have told you so far, there is a force acting. And we know the formula, force is mass times acceleration, which we can use to find the acceleration. But there is also a formula for force here, because it's a charged particle, namely the electron, entering that field. The force in this particular case is Q times E. So the force on a charged particle in an electric field is Q times E, where Q is the charge and E is the strength of the field. So we'll use that first. So F is equal to Q times E. Q is the charge of the electron, which is 1.6 times 10 to the negative 19. Again, will be given, but it's good to know the number. So, and the strength of the field or intensity of the field is the same thing, is 100. So when you do that, you will get 1.6 times 10 to the negative 17 newtons is the unit of force. And then we can find the acceleration using force by mass. We already got the force. Divide by the mass of the electron, which will again be given. It's 9.1 times 10 to the negative 31. So need not cram all those numbers, and just do the math. You get the acceleration to be really a big number. Comes out to be 1.76 times 10 to the 13 meter per second squared. All right, because the mass of the electron is so small, that's why we have that huge acceleration. All right, so what's to be remembered here is that the force on a charged particle in an electric field is Q times E. And then the general formula for force is F is equal to ma. So we've used both in this case. Which brings us to the next one. So the question is, what is the fundamental frequency of an open pipe of length 120 centimeters at 30 degrees Celsius if the speed of sound is 331 meter per second at 0 degrees Celsius? So we're asked to find the frequency at 30 degrees Celsius while the speed of sound at 0 is given. So first of all, we have to find the speed of sound at 30 degrees Celsius, okay? For that, we use this formula. Velocity or speed at 30 is equal to velocity at 0 plus 0.6 times T, where T is the temperature in Celsius, which is 30 in this case. So when we do that, we will get 349 because 0.6 times 30 is 18. So 349 meter per second. And once you get that, you also have to look carefully at, is this an open pipe or a closed pipe? In this case, it's an open pipe. If it's an open pipe, then the formula is for the nth frequency. So that's why I've written as F sub n. That means the nth frequency or the nth harmonic is NV by 2L. When you hear the word fundamental, you have to know n is 1. Again, for fundamental, n is 1. Therefore, all we need is just n is 1. We already found the speed of sound, which is 349 by 2 times the length. The length has to be in meters, not centimeters. So that's 1.2 meters, 120 divided by 100. So 1.2 meter, and we get 145.4 hertz. On the other hand, if this question was about a closed pipe, then the formula would have changed to NV by 4 times the length. So remember that, all right? So assuming that it's a closed pipe, I'm just doing that. Same thing again. If it was a closed pipe of the same length, and then we will find that the frequency, the fundamental frequency is going to be half of what we got here. Okay? Because the formula is NV by 4 times the length. So 1 times 349 divided by 4 times 1.2 will get us the answer, which is 72.7 hertz. So that is how we do that question. Let's move on to the next one. So in this one, I've not written it, this is to do with Doppler effect. And you see the observer moving towards the source. All right, do you see the observer there? Let me set this up, okay. The observer right there is moving towards the source at 10 meters per second, and the source is not moving, because you can see that from the velocity that's given. So the source is at rest. So velocity of the source is 0. Velocity of the observer is 10 meters per second. And this source produces a frequency of 3 kilohertz. Kilo is 1,000. So that is 3,000 hertz. And we have to find the frequency heard by the observer. So in Doppler effect, remember that when the observer moves towards the source, or the source moves towards the observer, or both move towards each other, the frequency always goes up. On the other hand, if they go away from each other, then the frequency goes down. So that's what you have to remember. In this case, the frequency is going to go up because the source is not moving and the observer is moving towards the source. Now, there is a general formula, which is on your formula sheet, which is F sub O, and that means the frequency heard by the observer, is F sub S, means the frequency actually produced by the source, is velocity of sound, that's velocity of sound plus or minus velocity of the observer divided by velocity of sound minus or plus velocity of the source. So if they are moving towards each other, use the plus in the numerator and use negative in the denominator. So if they're moving towards each other, again, very important, if they're moving towards each other, plus in numerator, minus in denominator. If they're moving away, then exactly the opposite. That means use minus in the numerator and plus in the denominator. Let's do this one and then you would understand. Okay, in this case, the observer is moving towards the source, so we're going to use plus in the numerator. And in the denominator, velocity of the source is 0 because it's not moving. So that means you just have to put these numbers plus V naught by, in the denominator you only have velocity of sound because V sub S is 0. All right, so the frequency actually produces 3 kilohertz, which is 3,000. That's why I've put 3,000 there. And the speed of sound would be given. It is, in this case, 350 meters per second. Again, that's given to you. So 350 plus 10 by 350 there. And when you do all that calculation, you get 3,085.7 hertz, which is, of course, more than the actual frequency produced. So that's how we do Doppler effect. I'm going to work out another question just to show you the difference. So in this case, look at the diagram. Now, the observer is moving at 10 meters per second towards the source, but the source is also moving at 20 meters per second towards the observer. So both are moving. On both of these accounts, the frequency goes up. So remember what I said, the numerator would be positive, the denominator would be negative. Okay. So there is the formula, again, the same formula. So plus or minus, I'm writing the general formula first. Okay. Now Fs is 3000 and 350 plus. So plus in the numerator, minus in the denominator. There you go. And do the math. So this time it's going to be much more than the last case. We get 3,272.7 hertz. Of course, as expected, because both are moving towards each other. So that's Doppler effect. Very important concept. Okay. Here's the next one. The sound intensity 6 meters from a source is 120 decibel. What is the intensity in watt per meter squared? Okay. So the conventional unit of sound intensity is watt per meter squared. But the practical unit is decibels. We have to know how to change from decibel into watt per meter squared. The formula is on the formula sheet. It is beta is equal to 10 log to the base 10. Oh, that's not log to the base c. I'm going to change that. It should be log to the base 10 I by 10 to the negative 12. So that's a constant. Remember that? And in this case, beta is 120. It's given. So again, 10 log to the base 10 I by 10 to the negative 12. So we're trying to find the value of I. So let me change that log to the base e to log to the base 10. Before that, okay, there. Let's change it. And I just brought this 10 to the other side, divided both sides by 10. That's why you have that divided by 10. And 120 by 10 is 12. So 12 is log to the base 10, I by 10 to the negative 12. Now, important, instead of putting log on the right side, we can put 10 raised to on the left side, which is what I'm doing now. So instead of so when we do that, you see that it becomes I is equal to 10 to the power 12 times 10 to the negative 12, which comes out to be 1 watt per meter squared. Okay, so 120 decibels is 1 watt per meter squared. Let's see why this distance was given. Actually, that was not used here. But in the next question, that's going to be used. It says the sound intensity 6 meters from a source is 120 decibel. At what distance is the intensity 90 decibel? Okay, so the first thing, you have to convert 120 and 90 into the conventional units of watt per meter squared. So we've already converted the 120 and we got 120 as 1 watt per meter squared. 90 decibel, we got to do the same way. We got to see how much it's going to be. And I'm using a shortcut here. If you don't understand, go back, refer the previous question. I know it's going to be 10 to the power 9 times 10 to the negative 12. Because it's going to be 90 by 10. 90 by 10 is 9, okay? So we get that as 10 to the negative 3 watt per meter squared, which is actually 0.001 watt per meter squared, isn't it? Okay, so that is at 6 meter, and how far away should you be so that the intensity is 0.001 watt per meter squared? So let us say it's at x meters. Remember now that the intensity is inversely proportional to the square of the distance. Inversely proportional, in the sense, if you move away from the source, if you double the distance, the intensity becomes 1/4. Double 1/4. Okay, if you move away from a loudspeaker, isn't the sound going to go down? That's what I'm talking about. So that's why it's I1 by I2 is R2 squared by R1 squared. We know the values of I1 is 1, I2 is 0.001, and then you have R2 squared here and 6 squared. Okay, so 1 by, that's actually 1000, 1 by 0.001, so I could have written it as 6 squared, 36 times 1000, which is 36,000. And so take the square root of 36,000 and you would get the answer. But the distance is going to be surprisingly big. It's 189.7 meter. Notice that? At 6 meters, it's 120. But to get the intensity down to 90 decibels, you have to move 189.7 meters. That's because this is a logarithmic scale, so be careful about that. All right, on to the next. This is talking about a closed pipe again, but remember the video lab that you did, where you got the first resonance at a particular length and then a second resonance after moving it a little bit more, a lot more actually. So we have two lengths, L1 and L2, that are given. This question says the first resonance occurs at 15 and the second resonance at 47 centimeter. So it's a closed pipe. We have to find the speed of sound in this particular gas. The frequency of the tuning fork is given, it's 256 hertz. You remember, we hold the tuning fork over that while we do the lab. So the first resonance is produced when the node is at the closed end and the antinode at the slightly outside the open end actually. So if you take the length of this pipe as L1, that's not going to be exactly equal to lambda by 4 because this antinode is just a bit outside. Let's call it E, that distance E. So we'll have to say L1 is, actually L1 plus E is equal to lambda by 4. So that's what I'm writing. L1 plus that slight distance E is equal to lambda by 4. Okay. And when you come to the second resonance, this is what you have. It's not drawn to scale. And there you're going to get 3 lambda by 4 because this is 3 parts. You see, the antinode node, that's 1 quarter. Again, the second quarter, and then the third. So 3 quarter. And fortunately, the end error E is the same. So L2 is 3 lambda by 4 plus E. In order to get rid of the E, we take the difference between them. When you take the difference between the two, on the left side you would get L2 minus L1. On the right side you would get E minus E, which will cancel out. And that's why we did it twice, just to get rid of the E. And then you would have 3 lambda by 4 minus lambda by 4. See that? 3 lambda by 4 minus lambda by 4 is actually lambda by 2. It's a 3 quarter minus quarter, which is half. Which gives us the formula lambda is 2 times L2 minus L1. When you rearrange, the 2 goes to this, multiplies. And then the speed of sound is F times lambda, where F is given, frequency 256. So into 2 times L2 minus L1. Well, remember both are in centimeters right now. So you're going to get the velocity in centimeter per second. Divide that by 100, you will get it in meter per second. So 163.84 meter per second. That is the answer that we get for that one. Shall we move on to the next? Okay. So in the next question, this is a direct application of Coulomb's law. Find the force between two 3 microcoulomb charges kept 7 centimeter apart in air. So you have the 2 charges, both are 3 microcoulomb and kept 7 centimeters apart, which is 0.07 meter. And to find the force, use Coulomb's law. What is that? F is K, Q1, Q2 by R squared. And we've used K before. K is 9 times 10 to the negative 9 times Q1. All right, 3 micro. What's micro? Micro is 10 to the power negative 6. So 3 times 10 to the power negative 6 times the same, because Q1 and Q2 both are the same, divided by 0.07 squared. Don't forget the square there. Do the calculations, you get 16.53 newtons. That's the answer. Let's move to the next one. What is the charge on a capacitor of 3 microfarad when charged to 10 volt? Straight application. Capacitors store charges. The capacitance is given and the voltage is given. How do you find the charge? Just go to the fundamental definition of capacitance. It's the ratio of charge to the voltage. And then rearrange that to make charge the subject, which would be now the product of capacitance and voltage. Capacitance is 3 micro, which is 3 times 10 to the negative 6. Voltage is 10, and you get the answer. It's such simple things and concepts that I want you to know. And there are many ways you could make a mistake, like forgetting to change the micro, or using the wrong conversion, or getting confused with the math. Try to avoid all that and you should be good. So 3 times 10 to the negative 5 coulombs. I think we've come to the last one. Have we? No, there's one more after this. Okay. Here, find the capacitance of a parallel plate capacitor with plate area 0.001 meter squared, separated by a material of thickness 0.1 millimeter. So, in a parallel plate capacitor, you have 2 parallel plates separated by a small distance. That distance is given. And the area of each plate is the same, and that's given. And it's filled with a material inside, which is an insulator, and the K, dielectric constant, okay, the K, this is not the same K as before. In this case, it's 1.5 given to you. And all you need to know is the formula for capacitance of a parallel plate capacitor, which is what? C is equal to K epsilon naught A by D. It's in your formula sheet. You just need to know K. Now remember, K is 1.5 given here. I've seen so many students write that as 9 times 10 to the 9. No, please, that's different. So K epsilon naught A by T. K is given. Epsilon naught, again, that is the permittivity of free space, will be given to you along with the question. It's just that I've not written it here, but it will be given. So that's epsilon naught. And then the area and the, all right, notice that I changed the millimeter into meter. I did. Divided it by 1,000 because 1,000 millimeters make a meter. That's why there are 3 more zeros. Okay. You do the calculation, you get 1.32 times 10 to the negative 12 farad. All right. Farad is the unit of capacitance. In this one, find the speed of an electron accelerated through 5 kilovolt. So when the electron enters the electric field, it's going to gain kinetic energy. I think everybody remembers the formula for kinetic energy. It's 1/2 mass times velocity squared. And that is equal to the product of the charge and the voltage. That's it. So 1/2 times mass times velocity squared is equal to Q times the voltage. Please remember, these are different V's. This is small, this is caps. One is velocity, the other is voltage. Okay. Again, the mass of the electron will be given, so that's there. Charge of the electron will be given, that's there. Q. Voltage is 5 kilo. It's kilovolt. So 1,000 So 5 times 1,000, 5,000. That's why that's 5,000. And then the rest is math. Just need to find velocity. So first we're getting the square of the velocity, and then we will take the square root to get the velocity. And in this type of problem, the velocity is going to be quite high because the mass of the electron is really small. It's going to be accelerated through very big velocities. So expect that answer. So this is what I found. The square of the velocity comes out to be 0.1758 times 10 to the 16. So when you take the square root of that number, you get 0.4, let's see, 0.42, okay, 0.42 times 10 to the 8 meter per second. That's what you get. Okay. 0.42 times 10 to the 8 meter per second. I thought that was the last one, but there's one more. No, there's two more actually. What is the potential 1 millimeter away from a charge of 1 nanocoulomb? So now we're trying to find the potential due to a point charge. The charge is given, the distance is given, and the formula is very dangerous. It's kq by r. There is no square. When you try to find the voltage, there is no square there. The square is only when you try to find the strength of the electric field. Please, please remember that. Again, K is 9 times 10 to the 9. Q is 1 nano. Nano is what? 10 to the negative 9. That's why you got 1 times 10 to the negative 9. Where did that 10 to the negative 3 come from? 1 millimeter is 1 by 1,000, and 1 by 1,000 is 10 to the negative 3. Sorry. And then you get 9,000 volts. There it is. Finally, we come to the last one. It's a combination of capacitors. And you have two capacitors here in parallel and one in series to that combination. And we are asked to find the equivalent capacitance, which means the total capacitance. So remember that when capacitors are in parallel, to find their total, just their total, you add them. So these two will result in 1 plus 2, 3 microfarad, right? Yeah. So C is C1, let me name them, C1, C2, and C3. So that's C1, this is C2, and this is C3. So first we're looking at C1 and C2. Because they are in parallel, just to add them. So that's 3. And then you have that 3 in series with the other 3. Okay, so then you have to use this formula. 1 by C equivalent is 1 by C plus 1 by C3. And it's 1 by 3 plus 1 by 3. Okay, it's both are 3. Because we got this is 3. And this is also 3. So that gives 1 by C equivalent is 2 by 3. But you got to take the reciprocal of that, reverse both sides. So you get it as 3 by 2 microfarad. That's how you do that. So those are the questions that I had for you in this review. Remember what I said at the beginning, there is no use of memorizing this. But if you take time to understand each quantity and really deliberately look at it and try to learn something from it and spend a couple of hours on this, you're going to do it on the exam. Thank you, and I hope you all have a good exam.